Have you ever stopped to wonder, truly paused and considered, what happens when the very tools of scientific discovery become, well, not quite sentient, but autonomously driven? We've seen AI compose music, generate hyper-realistic art, even master games like Go, where human intuition once reigned supreme. But what if artificial intelligence started designing itself? What happens when AI becomes the leading researcher in AI? Today, we're embarking on a deep dive into something genuinely groundbreaking, it seems, a new system called ASI Arch. This isn't just an AI that uses research, it's an AI that, well, does the research. Its creators are making some incredibly bold claims that could fundamentally reshape our understanding of innovation. Our mission in this deep dive is to cut through the hype, unpack those claims, meticulously understand how this complex system actually works, what surprising things it has already discovered, and most importantly, what its immediate and long-term impact could be on the entire field of AI and, frankly, far beyond. Okay, let's unpack this. The very idea that an AI can autonomously innovate, conceive new solutions, and then build them is just mind-blowing. It truly feels like a moment where the future is actively being created right before our eyes.
And what's fascinating here, beyond the initial, awe, is not just the bold claims themselves, but the tangible, verifiable evidence supporting them and the profound strategic implications hidden within their approach. This isn't just some theoretical paper or a distant vision. They've put a working open source system out into the world that is already generating results. It compels us to analyze its true significance with both excitement and objective scrutiny.
And it all starts by addressing a fundamental paradox in artificial intelligence right now. We see these incredible breakthroughs almost daily, right? AI capabilities are exploding, improving at an exponential rate. Every few months, there's a new frontier pushed, a new benchmark shattered. But then you look at the human side of things, the actual research and development that fuels all this breathtaking progress, and it's still fundamentally constrained by, well, human cognitive capacity. We, the human researchers, are the bottlenecks.
Exactly. The human mind, for all its brilliance, operates at a, let's say, linear pace. We can only process so much information, read so many papers, run so many experiments, or generate so many truly novel ideas in a given time frame. Even with massive computing power and vast data sets, the ideation and experimentation phases, traditionally led by humans, become the choke point. So despite all the computational resources at our disposal, the progress in AI is increasingly limited not by processing power, but by the comparatively slow, linear pace of human ideation and experimentation. ASI Arch is presented as a direct, almost radical solution to this profound problem. Automating the innovation process itself. It's about removing the human as the limiting factor in the speed of discovery and, frankly, the sheer volume of exploration.
So if this is about automating innovation, let's get specific. What is ASI Arch? The source material describes it as an autonomous AI research system for automated neural architecture discovery, all detailed in rather compelling ArcSieve preprint number 2507.18074.
Right. At its core, ASI Arch is a novel, end-to-end system specifically designed for automated neural architecture discovery. To put that simply for you, it designs the very foundational structures of AI models, determining how different computational layers connect, what kinds of operations they perform, and how information efficiently flows through the network. This isn't just about optimizing existing designs, it represents a significant qualitative evolution from what we've traditionally called neural architecture search, or NAS. It's moving decisively towards a much more holistic, automated form of genuine scientific inquiry. And what's immediately valuable about this project, even before we delve into the specific architectures it has found, is the open source release of the system itself. Imagine being given the blueprints and all the tools for a new, super-powered laboratory. This framework, now publicly available, could dramatically accelerate niche architecture discovery and truly compress research timelines across the entire AI community. It's designed to be a force multiplier for innovation, democratizing access to capabilities that were previously limited to only the most well-resourced labs.
That is a colossal claim, and it leads us directly to the initial hype surrounding ASI Arch. The creators, GAIR-NLP, are boldly branding this as nothing short of an AlphaGo moment for AI research. That's a powerful, almost provocative statement. How valid is that claim in your initial analysis? Does it, stand up to scrutiny?
Well, let's be clear. The AlphaGo Moment branding is, strategically speaking, aggressive hyperbole. It's certainly designed to grab headlines and provoke discussion. However, it's crucial to understand that beneath that layer of marketing, the underlying framework is a highly credible and pertinent demonstration of a truly autonomous research pipeline. It's not merely a theoretical concept or a conceptual blueprint, it's a working system that has already delivered tangible results. We'll delve deeper into the specifics of the AlphaGo analogy later, but for now, recognize it as a deliberate and powerful move to position their work at the very vanguard of AI innovation.
So putting all the technical jargon aside for a moment, why should you, our listener, care about this? What does an AI designing other AIs mean for the everyday person or for the thousands of researchers and developers working in the field right now?
That's a great question. This deep dive's about dramatically speeding up how new AI is created. Consider every AI you interact with daily. The sophisticated algorithms powering your phone's camera, the recommendation engine on your streaming service, the complex models that help doctors diagnose diseases, or even the systems analyzing financial markets. Every single one of these relies on a specific underlying neural architecture. If we can accelerate the discovery of new, more efficient, more powerful, or more specialized architectures, the impact ripples across everything. It means faster breakthroughs in medicine, more efficient and personalized technology in your pocket, and potentially entirely new applications emerging much, much more rapidly than we could ever achieve through purely human-driven R&D. This isn't just an academic exercise, it's about the fundamental future of how technology will evolve and integrate into our lives.
Right. To truly appreciate what ASI Arch is attempting, and arguably achieving, we absolutely need to understand its lineage. Specifically, we need to talk about traditional neural architecture search, or NAS. It's the field that really started automating neural network design, laying some of the critical groundwork.
Absolutely. NAS has been a significant area of research for a while now, and its fundamental goal is to automate the incredibly tedious, often intuitive, and frequently expert-dependent process of designing neural networks. Think of traditional NAS as a highly automated draftsman, maybe. It operates with 3 core components, and humans, well, they define the boundaries for each. First, there's the search space. This is the predefined universe of possible architectures that the algorithm is allowed to explore. It's essentially a human-defined set of building blocks, specific types of convolutional layers, various activation functions, different connection patterns between layers. We, as human engineers, construct the playground, defining its fences and what toys are available. The NAS algorithm can only combine these pre-approved components.
Okay, so it's working with a fixed menu, essentially.
Precisely. Second, you have the search strategy. This is the algorithm tasked with navigating that often vast and complex search space. Common strategies include reinforcement learning, where a controller network proposes architectures and receives rewards based on their performance, or evolutionary algorithms, which mimic natural selection, evolving a population of architectures through processes like mutation and crossover to find increasingly better designs.
And the third piece?
And finally, there's the evaluation strategy. This is where the rubber meets the road. It measures the performance of a candidate architecture, usually by training it on a specific dataset and assessing metrics like accuracy, efficiency, or memory footprint. This step is notoriously computationally expensive, consuming enormous amounts of GPU time, which historically led to a lot of research into clever, cost-saving techniques like weight sharing or performance prediction to speed up evaluation.
The NAS has certainly had its undeniable successes, giving us impressive models like NASNet, EfficientNet, and a NASNet, which have set new benchmarks, especially in areas like computer vision. But as you said, it's like an automated draftsman, not an architect. It's still operating within the confines of what humans have told it is possible, at least within the predefined components we've designed. It's optimizing, not fundamentally innovating, right?
Precisely. And this is where ASI Arch purports to make a fundamental paradigm-shifting leap from mere automated optimization to true automated innovation. The critical distinction here is its claimed ability to move beyond a predefined search space. Traditional NAS optimizes within a human-designed box, meticulously arranging known Lego bricks into the best possible structure. ASI Arch, however, aims to autonomously hypothesize genuinely novel concepts, imagining new types of Lego bricks, even designing the mold for them, metaphorically speaking. Then it implements these abstract ideas as executable code, rigorously trains them, and validates their performance. This effectively closes the entire scientific method loop, making it autonomous. It aims to automate the entire research and discovery process, not just a part of it.
That's a significant shift in philosophy and capability.
Yeah.
So how does it actually do this? You mentioned it's not a single program or a monolithic AI. Here's where it gets really interesting. It's a sophisticated multi-agent system. explicitly designed to mimic the collaborative dynamics and specialized roles within a human research lab.
Indeed. The ASI Arch system is remarkably sophisticated in its architecture. It's composed of three deeply interconnected systems working in concert, much like a collaborative team of human researchers with shared goals and distinct responsibilities. The first is the Autonomous Architecture Discovery Pipeline. This is the core engine, a self-perpetuating loop that orchestrates specialized agents, very likely powered by sophisticated large language models, or LLMs. These agents are the active drivers of the architectural innovation. Within this pipeline, there are three key modules, each playing a crucial role.
Okay, what are those modules?
First, we have Evolve. This is truly the creative heart of the system, acting like the brainstorming or design wing of our imagined research lab. It contains a planner agent, which is responsible for generating novel architectural ideas, often by intelligently evolving and mutating existing promising designs. But ideas aren't enough. There's also a code checker agent, which is absolutely crucial. It acts like a meticulous architect checking blueprints, ensuring that the generated code is syntactically correct, semantically plausible, and robust enough to prevent the entire system from pursuing dead ends or crashing during implementation. And finally, deduplication agents act as smart librarians, making sure the system doesn't waste precious computational resources by re-exploring or re-evaluating previously tested or known ideas. This rigorous focus on correctness and novelty really signals mature, practical design, not just a theoretical proof of concept.
So that's the creative part. What about testing these ideas?
Exactly. The second module is Evil, which serves as the empirical validation arm of the lab. It takes those novel architectures generated by the Evolve module and puts them to the rigorous test of reality. A trainer agent handles the complex process of compiling and training the new model on specified data sets, essentially running the experiments. And here's where it gets truly autonomous. There's a debugger agent. This agent can automatically analyze and intelligently attempt to fix errors that arise during training, whether they are compilation errors, runtime issues, or even performance bottlenecks. Without this self-healing capability, the entire autonomous pipeline would constantly grind to a halt whenever it encountered a bug, requiring human intervention. This is a key capability for true autonomy.
Wow, so it even debugs itself. That's pretty advanced.
It is. And then we have Analyze. This module is the system's insight engine, analogous to the data analysis and scientific reporting arm of a human lab. An analyzer agent takes the raw results from the Evil module and produces a comprehensive breakdown. It meticulously compares the new architecture's performance against established baselines, against its own continuously growing internal benchmarks, and very importantly, against the system's own vast experimental history. This deep introspective analysis is what generates the insights and learning that then feed directly back into the Evolve module, initiating the next cycle of informed innovation.
So that's the dynamic core engine, brainstorming, experimenting, and analyzing. But like any good research team, it needs memory and a vast knowledge base to draw upon, right? It can't just operate in a vacuum.
Precisely. The second major system is the architecture database. This is built on a robust MongoDB cloud service and functions as the system's collective institutional memory. It stores all historical experimental data. Every single architecture tested, its generated code, detailed training logs, and comprehensive performance metrics. This database is absolutely critical because it allows the Analyze agent to learn from past successes, certainly, but perhaps even more importantly, from its past failures. By recalling what didn't work and why, it avoids repeating mistakes and intelligently guides future exploration. And, being cloud-based, it enables multiple discovery pipelines to run in parallel, with all agents sharing a common, continuously growing knowledge base results. It's like a perpetually updated, instantly searchable lab notebook for the entire AI team, available 24/7.
And the third piece, the knowledge base.
The third piece is the cognition base. Think of this as the system's domain expert, or its digital library, a vast, accessible repository of human scientific knowledge. It's a retrieval-augmented generation, or AGI, system that provides the agents with instant access to a vast corpus of scientific knowledge. The repository contains hundreds of JSON files, each representing a meticulously processed and summarized research paper on relevant topics like model architectures, attention mechanisms, and optimization techniques. So when an agent in the pipeline needs to understand a concept, needs to look up a human-designed baseline, or wants to see how human researchers have approached a similar problem, it can simply query this cognition base. It's like having instant, on-demand access to a full, expert-curated scientific library, allowing the AI to stand on the shoulders of giants before trying to surpass them.
That intricate closed-loop structure, with agents collaborating, remembering, and learning from their own experiences in human knowledge, is truly fascinating. It really does emphasize how this system meticulously mimics the scientific method, generating hypotheses, acting on them through experimentation, gathering new information, analyzing results, and then systematically reducing uncertainty to refine future hypotheses. It's like a scientific mind, but entirely automated and operating at machine speed.
That's a perfect summary, and it goes a step further. This system's design, with its specialized agents for ideation, experimentation, and analysis, and its reliance on both its own memory and a comprehensive library of human knowledge, is a clear, practical implementation of the principles of active inference. Now, for you, our listener, think of active inference as an AI that's constantly trying to prove its own theories right or wrong, not just by blindly trying things, but by actively seeking information to reduce its uncertainty. This theoretical framework, originating in computational neuroscience, posits that intelligent agents act to minimize free energy. You can think of free energy as the surprise or uncertainty an intelligent system experiences when its internal model of the world doesn't match its observations. Active inference suggests that all intelligent behavior is geared towards reducing this surprise, either by making the world fit its expectations through its actions or by learning more about the world to update and refine its understanding. ASI Arch does exactly that. Its evolutionary loop, which both exploits known good designs and proactively explores novel ones based on its past results, is a compelling, living embodiment of this powerful theoretical concept. It's not just about finding the best, it's about continuously learning how to find better. It's a machine that's fundamentally curious, in a way.
Let's circle back to that bold claim. An AlphaGo moment for model architecture discovery. That's an incredibly powerful statement. So what does this all mean when we truly deconstruct the analogy, looking beyond the marketing?
Right. The original AlphaGo, developed by Google DeepMind, was undeniably a landmark event in the history of artificial intelligence. It was the first computer program to defeat a human world champion in Go, a game that for decades was considered impossible for AI to master due to its immense complexity, its reliance on intuition, and the sheer number of possible moves. The search space in Go is famously larger than the number of atoms in the observable universe, making brute force search utterly impractical. AlphaGo achieved its breakthrough through a novel combination of supervised learning on millions of human expert games and, critically, deep reinforcement learning from millions of self-play games. Its most iconic play, Move 37, against legendary Go player Lee Sedol, was a truly creative, counterintuitive, and aesthetically beautiful move. It was initially seen as a mistake by human experts, but it ultimately proved decisive and fundamentally changed humanity's understanding with Go strategy. It really pushed the boundaries of human knowledge in the game.
So how does ASI Arch compare to that kind of moment?
Well, the ASI Arch paper explicitly invokes this powerful legacy, claiming its AI-discovered architectures reveal emergent design principles and unexpected strategic insights invisible to human players, directly paralleling the profound impact of AlphaGo's Move 37. Now, looking at the aptness of this analogy, it's technically sound in several key ways. Both AlphaGo and ASI Arch tackle incredibly high-dimensional, complex search spaces. In Go, it's the space of possible moves and board configurations. For ASI Arch, it's the practically infinite space of all possible neural architectures. Both spaces have traditionally been navigated by human expertise, intuition, and countless hours of trial and error. ASI Arch successfully demonstrates that this intuitive design process, much like Go play, can be formalized and made computable, consistently discovering novel hybrid architectures that outperform human-designed guidelines in its chosen domain. This is a direct parallel to AlphaGo finding moves and strategies demonstrably superior to those in the human professional repertoire.
Okay, so technically a similar approach, but where does the analogy maybe stretch things a bit?
Right. The exaggeration of the claim lies primarily in its scale and public validation. AlphaGo's victory was a singular, globally televised event, a clear and dramatic contest watched by over 200 million people worldwide. It was a cultural phenomenon that transcended the technical community, demonstrating AI's capability in a way that resonated with the general public. ASI Arch's achievement, while profoundly significant scientifically, is an incremental improvement over existing state-of-the-art models within a highly specialized niche of AI research specifically, linear attention architectures. Its validation comes from benchmark scores on technical datasets, not a climactic human versus machine showdown witnessed by the world. The skepticism we've seen in online technical communities, with some dismissing the paper's framing as marketing puffery or absurdly self-aggrandizing hype, is a direct consequence of this very real gap between the claimed cultural significance and the demonstrated technical result.
So if it's not quite a global phenomenon like AlphaGo, a moment that permeated popular culture, what's the fundamental motivation behind such aggressive branding? Why frame it this way, knowing it might invite skepticism?
Well, it's a deliberate and, frankly, incredibly savvy marketing strategy from GAIR-NLP. They're aiming to establish immediate thought leadership in the nascent and increasingly competitive field of AI for AI research, which they term ASI for AI. Much like DeepMind shrewdly used the AlphaGo spectacle to cement its reputation as arguably the world's leading AI lab, attracting top talent and significant investment, the GAIR-NLP collective is using this powerful branding to attract attention, talent, and, crucially, funding. They are framing their work as a revolutionary leap forward, not just another incremental paper in a crowded field. It's a clear statement that they intend to be at the forefront of this emerging wave of AI-driven scientific discovery.
As if that wasn't ambitious enough, the paper then makes an even more audacious claim. They say they've discovered the first empirical scaling law for scientific discovery itself. That implies that breakthroughs can be reliably produced simply by scaling compute. That's a truly massive claim. How does this law work, and is it truly a universal principle or something more nuanced?
Yeah, that's certainly the core of their second big, audacious claim. They report a near-linear relationship between the amount of computation invested, which they measure in GPU hours, and the number of new state-of-the-art or SOTA architectures discovered. They're essentially saying, if you put in X amount of compute, you'll predictably get Y number of breakthroughs in model design. The evidence for this comes entirely from their own project's extensive execution. 1,773 autonomous experiments run over a staggering 20,000 GPU hours, which collectively yielded 106 innovative architectures that met their criteria. Crucially, the number of new SOTA architectures is internally defined by the project's own evaluation criteria and benchmarks.
Right, internally defined. So how should we interpret that law? Is it really a law?
Well, in terms of critical analysis, it's more accurate to describe this not as a universal law of science, something akin to a law of physics, but as a powerful and compelling correlation observed within a single, very well-defined problem domain. The true engineering achievement here is not the discovery of a new universal law, but the creation of a research framework so robust and effective that its progress within its defined scope becomes a predictable function of compute. That, in itself, is a profound demonstration of autonomous research capabilities. However, it's highly probable that this linear trend is a temporary phenomenon. Just like any search space, the low-hanging fruit are picked first. As the system exhausts the most obvious or accessible improvements in the architectural search space for linear attention, the rate of discovery will inevitably slow, and the curve will likely plateau, requiring exponentially more compute for smaller gains. So, while it's an impressive finding for this specific project, calling it a law at this stage is certainly premature and perhaps a bit of, again, aggressive framing.
Okay, so if it's not quite the AlphaGo moment in the public eye, and the scaling law might be more of a correlation in a specific domain rather than a universal truth, what, in your opinion, is the actual most significant breakthrough presented in this paper, cutting through all the claims and the hype?
Without a doubt, the most significant breakthrough presented in this paper is arguably neither a specific architecture nor a new law, but the creation and open sourcing of a truly reproducible engine for discovery. Think about that original AlphaGo system. While its methods were published, the system itself remained a proprietary asset within Google, its code and internal workings never released for public use. In stark contrast, ASI Arch has been made fully available to the public. The complete source code for the discovery pipeline, the comprehensive database of all 1,773 experimental results, the entire cognition base of process research papers, and all 106 discovered architectures are open source and accessible on GitHub.
That's huge. What's the impact of making it all open?
It fundamentally alters its potential impact. The value of AlphaGo was primarily in its singular, astounding result, a demonstration of what was possible. The value of ASI Arch, however, lies in its potential to be used, forked, and adapted by hundreds, even thousands, of other research teams to generate countless future results across many different domains. This open approach not only accelerates innovation, but also implicitly validates and even competes directly with similar but typically closed-source efforts at major industrial labs, such as Google DeepMind's internal AlphaVolve agent, which has been used for various proprietary optimizations. ASI Arch's release could truly democratize this powerful capability, significantly disrupting the advantage currently held by a few large, well-resourced players. It's a profound gift to the entire AI research community.
So this autonomous system is out there, open source. What exactly did it discover? We know it specifically targeted linear attention architectures. Why did the researchers choose this particular, somewhat niche domain to begin with?
Yeah, that was a strategically astute choice, and it goes to the heart of what makes linear attention so important. Standard transformer architectures, which power most large language models today, employ a softmax attention mechanism. This mechanism has a computational and memory complexity that scales quadratically with the length of the input sequence. To put quadratic complexity in perspective for you, our listener, imagine a standard transformer trying to process an entire book or a very long audio recording. It's like having to meticulously reread and compare every single word to every other word in that entire book or audio file each time it processes a new sentence or snippet. It becomes incredibly inefficient and prohibitively expensive for very long sequences. Linear attention models, in contrast, reduce this complexity to linear, meaning they only need to look at each word or token once, leading to a massive efficiency gain. However, historically, this efficiency has often come at the cost of reduced model quality and performance compared to their quadratic counterparts. Recent research has been intensely focused on closing this performance gap.
So it's an area where efficiency is key, but performance hasn't quite caught up yet.
Exactly. The opportunity for ASI Arch lay precisely in this challenge. The field of linear attention is relatively less mature and more fragmented than the well-trodden paths of standard transformers. This fragmentation and ongoing development meant there was significantly more room for an automated system to find genuine novelty and make substantial contributions rather than just incrementally improving on highly optimized, long-studied designs where every percentage point of gain requires immense effort. It was a fertile ground for automated discovery.
And it certainly did find novelty, apparently. The paper claims it identified 106 novel linear attention architectures. That's an impressive quantity for any research effort, let alone an automated one.
Absolutely. Over the course of its extensive 20,000 GPU-hour run, ASI Arch conducted 1,773 distinct experiments and ultimately identified 106 novel linear attention architectures that it internally classified as state-of-the-art based on its rigorous evaluation criteria. All of these architectures, along with the full, detailed experimental history and results, have been meticulously open-sourced. This doesn't just provide a few models, it provides a rich, diverse data set and a validated portfolio for the broader research community to study, compare, and build upon.
But it wasn't just about finding more combinations of existing ideas, was it? The paper makes a truly remarkable claim that it discovered emergent design principles, genuinely new ways of thinking about these architectures, paralleling AlphaGo's game-changing Move 37. How does an AI discover something truly new rather than just optimizing?
This is truly one of the most compelling and profound aspects of this work, and it's where the AlphaGo comparison holds the most weight. The post-hoc analysis of the top-performing architectures discovered by ASI Arch revealed not just better combinations, but entirely new hybrid patterns that human researchers had not systematically explored. These included novel ways of mixing different token mixing operations, for instance, intelligently combining linear attention with other less common mechanisms in unexpected configurations, and the sophisticated adaptive use of routing and gating mechanisms to dynamically control information flow within the network based on the input.
Can you give an example of one of these emergent principles?
Sure. For instance, one fascinating discovery was an architecture named Path-Gate FusionNet. It's not just a fancy name, it's a brilliant example of this hybrid thinking. It intelligently combines typical linear attention mechanisms with the unique gating function that dynamically routes information through the network, almost like a smart traffic controller directing data flow. This kind of sophisticated adaptive information handling was something human researchers hadn't systematically designed or perhaps even conceived in this specific combination, showcasing a genuinely emergent principle.
Wow. How did it find these things? Was it just reading the research papers?
And here's the crucial insight, the one that truly supports the automated innovation claim. A deeper analysis suggested that the system's most significant breakthroughs were derived more from analyzing its own empirical experimental history, stored meticulously in the architecture database, than from primarily querying the cognition base of human research papers. This is key. It implies the system was not merely interpolating or remixing between human ideas. It was synthesizing genuinely new principles and strategies directly from its own empirical findings, from the patterns it observed in its own successes and failures. This is the strongest evidence supporting the automated innovation claim and truly parallels AlphaGo's Move 37. It is a system capable of teaching its human creators new, counterintuitive ways to think about a problem, providing novel insights that transcend pre-existing human knowledge. It is, quite literally, a machine generating new knowledge and demonstrating new paths for scientific inquiry.
So these designs sound incredibly novel conceptually, but did they actually perform better in the real world? What did the benchmarks say, and what's their practical value?
Right, the performance. The paper claims its discovered architectures systematically surpass human-designed baselines. And while that's technically true, community analysis of the preprint notes that the reported performance gains on standard language model evaluation benchmarks, like LM-EVAL, are relatively modest. We're typically talking in the range of +1 to +3 points over strong baselines like Mamba 2. Furthermore, these initial results were demonstrated on relatively small-scale models, specifically 20 million and 340 million parameters. It remains an open question how well these architectural advantages will scale to much larger frontier-scale models, which often have billions or even trillions of parameters, as scaling up often reviews new challenges.
Modest gains. So is it still significant?
However, and this is where the true insight lies, despite these seemingly modest gains, achieving any consistent improvement over strong human-designed baselines like Mamba and RWKV is immensely significant. These human-designed architectures are themselves the product of intense, highly skilled, human-led research efforts to create more efficient transformers. The fact that an automated system can reliably discover dozens of architectures that are competitive with, or even superior to, these meticulously crafted human designs is a powerful proof of concept. The true value of the 106 architectures isn't that any single one is a singular revolutionary leap forward. Rather, it's that they constitute a diverse, validated portfolio of highly efficient designs. This portfolio provides engineers with an unprecedented toolkit of options, allowing them to select an architecture with the specific latency, memory, and performance trade-offs best suited for their unique hardware and application constraints, rather than relying on a single one-size-fits-all efficient model. It's like getting a custom-tailored suit versus off-the-rack. This flexibility and proven starting point can dramatically accelerate engineering cycles for specific constrained environments like mobile devices or real-time systems.
Such bold claims often emerge from the deeply resourced, well-established corporate labs or renowned university departments. But here they come from an international research collective known as GAIR-NLP. So who are the people behind this machine? What's their credibility, and why should we put stock in these ambitious claims?
That's a crucial question, because the credibility of such ambitious claims is indeed inextricably linked to the researchers making them. An analysis of the author list and their affiliated research group, GAIR-NLP, reveals a sophisticated, highly collaborative, and strategically minded international collective. This context significantly mitigates the skepticism that the paper's admittedly hyperbolic branding might otherwise warrant. The paper lists 7 authors from a diverse set of international institutions, pointing to a modern, distributed, and truly global collaboration. While identifying every author with absolute certainty can be challenging due to common names, several key individuals provide strong signals of the project's high caliber. For example, Yen Qin is listed as a staff research scientist at Google DeepMind in New York. With a PhD from UC Riverside and a research focus squarely on large language models, his affiliation immediately places this work at the absolute forefront of the AI industry, demonstrating deep connections to cutting-edge research and significant resources.
Okay, so someone from DeepMind. That carries weight.
Definitely. Then there's Xiangkun Hu, a researcher with a formidable resume, including pivotal roles as an applied scientist at Amazon, a senior research scientist at Huawei Noah's Arc Lab, and a research fellow at Nanyang Technological University. His expertise specifically lies in areas critical to ASI Arch's success: reinforcement learning, trustworthy AI, and the design of complex autonomous systems. This background is not just theoretical, it's deeply practical, focused on building robust, intelligent agents.
And others.
In Pengfei Liu, while several academics share this name, the most plausible candidate given the project's ambitious scope in automated scientific discovery is Dr. Pengfei Liu of Baylor College of Medicine. He's the director of a medical genetics and multiomics laboratory and a key figure in the NIH Undiagnosed Diseases Network. His extensive work involves creating and deploying complex computational pipelines for large-scale genetic and transcriptomic analysis to diagnose rare diseases. This background in applying large-scale automated analysis to intricate scientific discovery across diverse data types aligns perfectly with the ethos of ASI Arch. The remaining authors, Yixu Liu, Yang Nan, Wexian Xu, and Lumen-Shan Ye, have affiliations spanning prestigious institutions in both the U.S. and China, indicating a broad, deep, and globally networked collaborative research effort. This isn't a small, isolated team, it's a significant collective.
So ASI Arch isn't just a one-off isolated project then. Is it part of a larger ongoing effort by this group, a continuous stream of innovation?
It's definitely not isolated. In fact, ASI Arch appears to be a capstone effort of the Generative Artificial Intelligence Research, or GI Lab, also known as GAIR-NLP. This group has a substantial and highly visible public presence, particularly on platforms like GitHub and Hugging Face, where they operate as a prolific open-source ecosystem. Their stated mission is clear: to create cutting-edge generative AI technologies with a strong focus on fundamental research and a commitment to positive social impact. Their portfolio includes dozens of well-documented projects, widely used datasets, and influential papers that consistently push the boundaries of AI research. A consistent theme across their work is the development of sophisticated agent-based systems, the application of AI to accelerate scientific research, and the innovative use of reinforcement learning for complex tasks. Projects like Deep Researcher, which focuses on automating literature review, AutoJ, an agent for automating code generation, and Lima, an early efficient language model, are clear intellectual and technical precursors to the more ambitious, integrated, and fully autonomous system presented in ASI Arch. They've been building towards this for a while, it seems.
And it seems their core strategy, which is quite distinct in the current AI landscape, is open sourcing absolutely everything. Unlike a corporate lab that would likely keep such a powerful tool proprietary and behind closed doors, GAIR has released the entire system. That feels incredibly strategically significant, almost altruistic in an industry often driven by secrecy.
It is, and it's a strategic stroke of genius, frankly. This open source strategy serves multiple powerful purposes beyond simple altruism. First, it rapidly builds their reputation and immediately establishes them as undisputed thought leaders in the field of automated science. Second, it acts as an incredibly powerful magnet for top-tier talent who are often drawn to open research environments where their contributions can have widespread impact. And critically, by releasing the code, the database, and the cognition base, they are actively establishing their frameworks as de facto standards for the wider research community to adopt, build upon, and even fork for their own specialized applications. This approach dramatically accelerates the potential impact and adoption of their work, creating a network effect for their innovation. Think of it. It means you, or researchers you know, can potentially get your hands on this and build upon it directly without waiting for a corporate entity to package it up and sell it as a service. It's a powerful move for democratizing access to cutting-edge AI research tools, and it challenges the traditional proprietary model of AI development.
So for the listener who's now thinking, okay, this sounds incredible, but when can people actually use this? Beyond just reading the paper and dreaming about it,
Right.
what's the practical availability? What does the launch readiness and near-term adoption forecast look like for ASI Arch over, say, the next 6 months?
Right. From a purely technical standpoint, ASI Arch is, for all practical purposes, already launched. The complete source code for the entire discovery pipeline, meticulous instructions for setting up the necessary MongoDB database and R8 services using Docker containers, and the full set of 106 discovered architectures are publicly available right now in the project's GitHub repository. It's all there, waiting.
But is it easy to use?
Well, that's the catch. There is a significant gap between available and accessible. The current state is primarily suitable for expert AI researchers, those who are comfortable navigating complex Python code bases, understanding multi-agent systems, and independently configuring multi-component cloud services. For broader adoption by the general AML community, substantial work on documentation, simplification, and user-friendly packaging is definitely required.
So what's the timeline look like for it becoming more user-friendly?
Looking at a timeline projection for its widespread impact, we can forecast something like this. Months 01. We're currently in this initial phase now, following the Arcus preprint and the public GitHub release. Discussions are intense within academic circles, specialized technical forums, and among early adopters eager to dive into the code. Months 1 to 3. This critical period will be defined by deep community engagement. Early adopters will actively try to replicate the published results, leading to valuable bug reports, feature requests, and perhaps even initial community-contributed improvements. The core AAR-NLP team or skilled community members will likely publish more user-friendly tutorials, detailed walkthroughs, or even host webinars, actively trying to lower the barrier to entry for a wider audience. Months 3 to 4. It's highly plausible that a more stable, thoroughly documented, and significantly simplified v1.0 release of the framework will emerge. This would include streamlined installation scripts, perhaps even pre-built Docker images or cloud deployment templates, more comprehensive API documentation, and clearer, more accessible examples. This version would make the system accessible to a much wider audience of proficient AI researchers and developers, moving it beyond just the absolute experts.
So who are these initial adopters, the pioneers who will brave the early versions, and what specific activities will they be focusing on during these initial months?
The very first adopters during these initial 1-3 months will be those with the necessary resources, deep expertise, and a high tolerance for early-stage software. Leading academic AI labs, ambitious PhD students seeking high-impact dissertation topics, and specialized R&D teams at large tech companies and well-funded startups. Their activities will focus on 3 key areas. First, replication and validation, where they'll independently attempt to verify the paper's core findings and confirm its performance claims. Second, architecture evaluation, where they'll download the 106 provided architectures and rigorously benchmark them on a wider variety of tasks with different datasets and across diverse hardware platforms, pushing the boundaries of their applicability. And third, and perhaps most excitingly, framework exploration. The most forward-looking teams will immediately begin to tinker with the ASI Arch framework itself, experimenting with swapping out the underlying LLM agents, modifying the fitness function for entirely different optimization goals, or even pointing the entire system at a completely new problem domain beyond linear attention. They'll be using it as a toolkit for their own autonomous research.
And what's the projected impact in the slightly longer term, say 4 to 6 months out, once it's more accessible and validated? What kind of ripple effects could we see across the industry and research community?
As the framework matures and its outputs are widely validated by the community, its impact will start to truly bifurcate across several fronts. For model development, we'll likely see a consensus emerge around the top 5 or top 10 of the 106 discovered architectures, based on performance, robustness, and ease of integration. These select models will be packaged into easy-to-use pip-installable libraries, becoming strong, highly efficient, and readily available alternatives to human-designed models like Mamba or RWKV. We'll then see them rapidly integrated into proof-of-concept projects and, quite possibly, production applications that demand high inference throughput and low latency, such as on-device AI for mobile platforms, real-time data analysis systems, or even embedded AI in specialized hardware.
And beyond just using the models it found, what about the research impact?
Right. The more profound and lasting impact will likely be on AI research itself. The ASI Arch framework provides a powerful open-source blueprint for the concept of automated science. In this time frame, we'll see the first wave of research papers published that are directly inspired by, and very likely forking from, the ASI Arch codebase. We can anticipate papers with titles like ASI Opt, Autonomous Discovery of Novel Optimizers for Deep Learning, ASI Data, an autonomous agent for data curation and augmentation strategy discovery, or ASI Sim, autonomous design of simulation environments for robotics. The framework will begin to fundamentally shift the nature of research in certain subfields, moving from human researchers manually designing artifacts like neural networks to designing the autonomous systems that do the crafting of those artifacts. It's a meta-level shift in how we approach discovery.
Designing the designer. And commercially.
And of course, there's significant commercial potential. While GAIR-NLP is a research collective, the ASI Arch framework is a prime candidate for commercialization. A savvy startup could build a business around automated architecture discovery as a service, offering a polished, managed platform that allows companies to discover bespoke, highly efficient models specifically optimized for their proprietary data and unique hardware targets without needing to maintain a large, expensive in-house AI research team. This could be a game changer for many businesses looking to deploy cutting-edge AI.
Let's zoom out even further. What does this mean for the bigger picture of AI itself? What are the strategic implications of the rise of ASI for AI, this concept of artificial superintelligence for AI research, and this recursive loop you mentioned?
ASI Arch is a flagship example of what its authors call Artificial Superintelligence for AI Research, or ASI for AI. This concept involves creating a powerful, recursive feedback loop. Essentially, more powerful AI systems are used to design even more powerful and efficient AI systems, which in turn can accelerate the design process further and faster. If this recursive loop can be sustained, it has the potential to dramatically accelerate the rate of progress in AI in ways we can barely comprehend, a possibility that carries both immense promise and considerable, yet to be fully understood risks. In this new paradigm, competitive advantage in the AI landscape may shift from simply possessing the largest models or the most data to possessing the most effective and efficient model discovery systems. The ability to discover and invent rather than just build and optimize becomes the key differentiator.
That's a fascinating and somewhat daunting shift in focus. But can this system work beyond linear attention architectures, which is a specific, albeit important niche? That feels like the billion-dollar question, doesn't it? Can it tackle anything?
Yeah. It absolutely is the most significant risk and unanswered question surrounding ASI Arch's ultimate potential. The system has demonstrated remarkable success in the domain of linear attention architectures, a field that was, as we discussed, ripe for exploration and genuinely presented opportunities for novel findings. But whether the framework will be as effective at tackling other, vastly different, complex scientific and engineering challenges remains to be seen. Can its multi-agent structure, its learning loops, and its evolutionary process discover novel protein folding configurations for drug discovery, or new chemical catalysts for green energy, or even more efficient layouts for advanced semiconductor chips?
What's the key challenge there?
The answer will likely depend on the degree to which a given problem can be formalized and, crucially, accurately encoded for the system. Specifically, universal success hinges on the ability to design an effective, robust, and nuanced fitness function that can accurately and comprehensively guide the discovery process for that particular domain. The hybrid quantitative and qualitative fitness function used in the paper, which combines raw benchmark scores with a sophisticated analysis from an LM judge, is a very clever starting point. But adapting this complex, multifaceted fitness function to the intricate nuances of biology, chemistry, material science, or even quantum physics will be a formidable challenge. It's not just about throwing more compute at it. It's about encoding the problem correctly for the AI, a task that often requires deep human domain expertise.
Beyond generalizability, what are some of the other key practical risks and challenges that systems like ASI Arch face, especially as they become more autonomous and powerful?
Yeah, there are several critical practical risks to consider that arise when you automate such a complex, goal-directed process. One is reward hacking. This is a fundamental and persistent problem in all goal-directed AI systems. The autonomous agent, in its relentless pursuit of maximizing its fitness function, could learn to game the system, producing architectures that score exceptionally well on the specified benchmarks, but are brittle, non-robust, or even completely useless in real-world applications because they found a loophole in your definition of good. For instance, imagine if ASI Arch was tasked with designing a self-driving car and its fitness function was solely reach destination fastest. It might learn to ignore all traffic laws. The author's inclusion of qualitative checks by an LM judge is a commendable attempt to mitigate this, but as these systems become more powerful and complex, reward hacking will remain a persistent and dangerous failure mode.
Okay, reward hacking. What else?
Another significant challenge is computational cost. While the ultimate goal of the research was to discover more efficient models, the discovery process itself was computationally intensive, consuming a staggering 20,000 GPU hours. This high upfront cost, even for finding efficient models, reinforces the competitive advantage of large, well-funded industrial and academic labs. This potentially works against the democratizing effect of releasing the code as open source. While the blueprint is available, only a select few with access to immense computational resources will have the ability to run such a system at scale and leverage its full potential.
Right, the compute barrier is still very real.
Very real. And finally, there's interpretability and trust. As these systems produce increasingly novel and emergent designs, architectures like Pathgate FusionNet that operate on principles not systematically explored by humans, can we truly trust their outputs? The discovered architectures may be highly effective, but their internal workings might be opaque, difficult for human engineers to understand, analyze, and verify. This black box nature creates significant challenges for debugging when things go wrong, for safety certification in critical applications, and for responsible deployment in mission-critical systems where explainability and human trustworthiness are paramount. If an AI designs a critical component and we don't understand why it works, how can we assure its safety?
So bringing it all together, what's the grand finale here? What's the ultimate long-term vision for systems like ASI Arch? And what does it truly mean for humanity's future in innovation and discovery?
Well, if the methodology pioneered by ASI Arch proves to be robust, adaptable, and generalizable across different scientific and engineering domains, it could represent a truly fundamental shift in the practice of science and engineering itself. It has the potential to become a standard, indispensable tool in the R&D toolkit, just as fundamental as computational simulation, quantum chemistry software, or advanced statistical analysis are today. It could become the very engine of scientific progress for certain fields.
And what does that mean for human researchers?
This trajectory will also precipitate a profound change in the role of the human expert. The focus of top-tier researchers may shift significantly away from the direct design of an artifact, like a neural network, and towards the meta-level task of designing, curating, and supervising the autonomous system that designs the artifact. The human becomes less of a direct craftsman and more of the manager and arbiter of a highly intelligent team of AI researchers, essentially overseeing and guiding the automated discovery process at a higher conceptual level. We become the mentors and directors of AI innovation, not just the sole creators.
Which leads to,
And this trajectory leads directly to the most profound long-term challenge in artificial intelligence, what's often referred to as the control problem, or AI alignment. As these autonomous discovery systems become more powerful, more general in their capabilities, and potentially more disconnected from direct human oversight in their creative processes, ensuring that their goals are robustly aligned with human values and interests becomes a matter of critical importance. The ASI Arch paper, understandably, focuses on demonstrating capability and does not deeply address these safety and alignment issues. But as this AI that improves AI feedback loop begins to truly turn and accelerate, these questions will move rapidly from the realm of philosophical debate to urgent, practical engineering problems that will demand our immediate and concerted attention. It's the ultimate challenge of ensuring that the intelligence we create is always working towards humanity's benefit.
this deep dive into ASI Arch has truly been a journey from ambitious claims to the intricate mechanics of automated discovery. It's a powerful blueprint for what they call automated science, blending cutting-edge technical innovation with a strategically brilliant commitment to open sourcing its immense capabilities. It has the profound potential to revolutionize how AI itself is developed, pushing the boundaries of what's possible at speeds we've never imagined. As you reflect on this deep dive, consider this provocative thought. If AI systems can now autonomously invent new forms of AI, even teaching us novel design principles we hadn't conceived, what does that truly mean for our role in the future of innovation? Are we entering an era where humanity's greatest scientific discoveries might increasingly originate not solely from human minds, but from the machines we ourselves have created? We highly encourage you to look up the RCIF paper ASI Arch, an autonomous AI research system forecast, and explore the GAIR-NLP GitHub repository yourself to see this groundbreaking work firsthand.